Assalamualaikum and hi again. We are again to the last part of Introduction to Cathodic Protection, part 3 of 3. So this is a sample of the zinc sacrificial anode being used for a small boat, which is directly connected to the hull of the small boat, the underside of the hull of the small boat. So today we'll be going to part 3 of 3, which is the last part for this cathodic protection introduction. We will be going through soil resistivity test, interference and its mitigations with regards to the impressed current type cathodic protection, earthing and ICCP, maintenance strategies, so how do we test and check whether it is acceptable or not, and the CP design considerations in general. So before going into cathodic protection, so initially we've talked about the soil resistivity being part of the design consideration for the selection or the sizing of your cathodic protection. So how do we actually test your soil resistivity? So for those of electrical background, I'm sure you are familiar with the Weinner method or the 4-point method, 4-pin method. So the meter will gives out resistance R, so you will calculate the soil resistivity equals to 2 times pi times A times R. So the A is the distance between the equal distance between each spikes. So you have 4 spikes, or 4 points. 1, 2, 3, 4. So you have your P1 and C1, P2 and C2 . So P stands for potential or your voltage, whereas your C is your current . So your equipment here will inject a current, DC current, and this potential P1 will measure the potential. Same goes for P2 . So the resistance is basically the measured potential over your injected current. So that is your resistance. So for you to know the soil resistivity at 1 meter, so you will put your 1 meter means 1 meter depth. You will put your spike at 1 meter distance between each spike. So you will repeat this up to maybe 30 or 40 feet or 20 to 30 meters. Depends on if you are going to install a deep well. So normally you go up to even 30 to 40 meters. So you'll do this, for example, maybe you do every 2 or 5 meters. So every 5 meters, you will measure. You will put the spikes in between the distance between each spike 5 meters apart. So you measure the resistance. So you will calculate the resistivity at 5 meter depth. Same goes for 10 meter depth and 50 meters. So you will get the soil resistivity, which is ohm meter, because ohm times the A, which is your meter in meters. So you'll have a lot of reading. So depending on the best soil resistivity condition, you will decide which depth is the best for you to install your anode bed. Okay. Alright. So we use a Weinner 4-pin method to perform the soil test procedure. So if your resistivity range is, for example, if the soil resistivity range is up to 10 ohm meter, so severely corrosive, then 10 to 50 corrosive, 50 to 100 moderately corrosive, 100 and above is slightly corrosive. Alright, so these are a few standards. This is based on British Standard 7361, whereas this one is based on API. So API is, I would say, more lenient as compared to the British Standard. So 5 to 10, it just consider this as corrosive, whereas up to 10 is severely corrosive for based on British Standard. Okay, but this is just categorization . In the end, you will select whatever resistivity range that you will select depending on the type of anode that you want to use. Then you will size accordingly, the size of the anode. So second part is the interference. Where does this interference come from? The easiest is other ICCPs, other impressed current cathodic protection. For example, like in the cathodic potential layout that I've shown you in part 2 of 3 of this module, that you can see that there is more than one ICCP in a plant because the fire water pipeline is going all around the plant. So maybe the fire water pipeline part 1 is being protected by ICCP number 1, whereas for ICCP number 2 is being protected by, the fire water pipeline number 2 is being protected by ICCP number 2. So this ICCP number 1 can interfere with ICCP number 2 and vice versa lah. So it can make your pipeline to be underprotected or overprotected. So other sources can be transit or mining system, HVDC transmission because of the DC, and also magnetic disturbances. This is the natural magnetic disturbances in the environment. Normally during lightning or due to the charges within the earth itself. So the easiest mitigation is bonding resistance. This one is normally used to mitigate the problems when we have too many ICCPs near to each other. The second way is sacrificial anodes at the unprotected area. Okay, and also we can use sacrificial anodes such as zinc ribbon to block any HVDC or interference from the transit or HVDC or magnetic. So basically, between your pipeline and the sources, for example, if you have a nearby HVDC transmission or nearby mining system or nearby transmission line, so you can put this zinc ribbon along the way to become, but this zinc ribbon is also a type of sacrificial anode, so this zinc ribbon will sort of sacrifice itself and block this interference from these three. For ICCPs, we will use a bonding resistant. So between protected and foreign pipelines, we will use a bonding resistant. It's very simple. You'll have two pipelines connected through thermowell. Then it goes up above ground to a bonding box. Inside the bonding box, we will have a resistor. We call it a bonding resistor. So it's normally green color or white color. It's made of mica. This is a high temperature resistor. High temperature resistor. So we'll also have a shunt, 50 millivolt, 50 amps. Shunt is basically to measure the current going from pipeline 1 to pipeline 2, or from pipeline 2 to pipeline 1. So once you during the commissioning of the second pipeline, so you will control this pipeline. You will control the current flowing from the new pipeline to the old pipeline through this bonding resistor by adjusting the resistor to go higher or lower. Okay. So these are some of the harder part for the cathodic protection companies to do commissioning Because if they have installed new pipe along 3 old pipes and they have separate ICCPs, it's quite troublesome because they not only have to commission the new cathodic protection but also the old cathodic protection. Because it's very complicated. I mean, if those who have been from the cathodic protection industry would know the complication of that. And influence on the earning system. For example, let's say the first case, we have an pipe without any cathodic protection. Let's say there is an exposed, the metal pipe is exposed due to the coating defect. So this ferrum, this earth will become your electrolyte, and there's a nearby earth electrode. So this earth electrode copper will become your cathode, and the ferrum here will become your anode. So your anode, your copper, your metal pipe will corrode until it punctures until it breaks. But your earth electrode copper will be protected Okay, so this is more like a corrosion cell. So you have your anode here, your cathode here, and your anode ferrum here. So you have your electrolyte, which is your soil, all around here. So this is sacrificial type anode. So if you have a copper also nearby a protected pipe with a sacrificial anode, because if your protected pipe is ferrum and your earth electrode is copper, so your sacrificial anode or your galvanized steel may not only protect your pipe but also your copper. For example, your copper earding. By right, you have only sized the surface area of your protected pipe only, and not include the surface area of earth electrode. So your anode will deplete much faster lah, because of the copper earth electrode. So what can you do is, for your earding, please use other type of material which will not be affected by the sacrificial anode or the ICCP. So as in the standards and many standards, they propose to use galvanized steel lah, as your earth electrode. Alright, because the earth electrode will be almost the same potential as your anode. So the anode will not be protecting anything which is about the same voltage as it is lah, or same potential lah. And also, if you are connecting two dissimilar metal of earth, you will also create a corrosion cell. This is why we call it as a galvanic corrosion. So you have your earth electrode galvanized steel and your copper. So in the long run, your galvanized steel will deplete because of corrosion. So it will sacrifice itself to protect the copper earth electrode. So this is a simple corrosion cell. Okay, maintenance strategy may differ from one another. This is based on the M plan or the maintenance plan that we've experienced previously. For monthly, normally we will only check the TRU or the transformer rectifier unit voltage and current readings. Quarterly, we will still check transformer unit voltage and current readings, cable tightness, piping. So test points will be measured in terms of its on and instant off potential. So what do you do is actually at your transformer rectifier, you will install a timer. So the timer will switch on and off your TRU. So the on is basically you will measure the test point between the test point to the copper sulfate reference point, and you will measure during the on condition and also during the instant off. Instant off is basically when the TRU is immediately off lah. You want to see whether the charges are still being contained or not. If the voltage at the touch point drops drastically, it means there may be some leakage along the pipeline or near that touch point. Then you will also measure the current drain measurement at the bonding cables. This one is between the bonding resistor and then bonding cable tightness. And anode bed, you will individually measure the anode current output, because from here you will know whether the anode is still there or has it depleted too much. 2 yearly, you will also do a CIPS or closed interval potential survey. This one, it is similar to a test point using a test point, but test point, for example, a long pipeline is normally located every kilometer. But CIPS, the guy will walk with his heavy bag and bring 2 sticks and measure the potential along the pipeline from the nearest test point. Then he will walk every meter or every 5 meters, then measure. Then walk another 5 meters, then measure again. And the last part is the DC voltage gradient. So this DC voltage gradient is the piping coating survey. So in a way, it can detect if there is any coating damage along the pipeline. So you will go along the right of way on top of the pipeline. The guy will walk and measure all along. Let's see. So this is a closed interval potential survey. So one side will be connected to the test post, which is your negative of the voltmeter. So this voltmeter is already equipped with a data logger. If no data logger, then you have to manually record it. Then the positive of the voltmeter is connected to the reference electrode, normally copper sulfate. Okay, so you will record the on and the instant off with the help of GPS, current interrupter. So this current interrupter is normally installed near the transformer rectifier unit. So we record, so we see the voltage is supposed to hold almost uniformly between, for example, if it is on voltage, it should not drop, it should not be more than 3000 millivolt, 3 or 2.5 to 3 volts. Whereas the instant off should be between 850 to 150, 1.15 volts. So if there's a sudden drop, it may be showing a potential area with coating defect or pipeline defect. Okay, defect. Okay, so it could also be due to soil variance. All right, it could also be due to others For example, if there's a contact, when there's a metal to metal contact, so this metal contact will require extra protection. So the current will through here will be much more, so the voltage drop will be much higher. Okay, so this is CIPS reading taken every 1 to 5 meters interval. So why instant off measurement? Why do you take the instant off measurement? So with the on measurement, the reading includes the IR, or the current times resistance drop error caused by the flow of the CP currents in the soil. So when you measure the instant off, so this IR is eliminated, this VIR. So that's why you look at the instant off. So in a way, if the instant off drops drastically, you know that there's some defect near that area that you have measured. So for the CP acceptance criteria, the on is between minus 850 millivolts to minus 3000 millivolts, depends on the quality of the coating. Instant off for a copper sulfate reference is 850 to 1150. Depolarization of minimum 100 millivolt means the instant off voltage minus the native voltage should be more than 100 millivolt. Okay, so the native voltage is, how do you get the native voltage? You must leave the ICCP turn off for at least 3 to 14 days. Then you measure back. So the instant off difference and the native voltage must be more than 100 millivolts. Potential shift is basically on voltage minus negative potential must be more than 300 millivolts. So this is the CP acceptance criteria. So this is this is the old acceptance criteria. I'm not sure if there's any new standards. So this was based on the data, the work that we've done, I would say about almost 10 years back. So if there's any new acceptance criteria, please do share with me in the comments below, or you can email me to cruxofe@gmail.com. Alright. So overprotection of coated pipelines. Overvoltage or overprotection of the structure leading to coating disbondment, or we call it, they call it as the holiday effect. So what do you mean by overvoltage? So overvoltage here means, like we say, when the ICCP is in the on condition, it must be not more than 3 volts or 3000 millivolts. So if there's some area where the voltage is more than 3 volts or 3000 millivolts, it could cause the coating to be disbonded from the pipeline surface. So why? Because this holiday effect, this will produce hydrogen between the coating and the piping surface. So this bubble of hydrogen will accumulate until it pops the coating. So the coating bubbles up, the hydrogen bubbles up and breaks away from the pipe, so exposing the coating damage. So you cannot protect your pipeline. Okay, unless there's a new coating that can last for voltages more than 3 volts in the long run or during its lifetime. And this is DCVG. DCVG is the direct current voltage gradient inspection department. So this is not under electrical per se. This one, inspection or the material corrosion team, they will do this. So the DC voltage gradient or DCVG is used to locate defects or faults on the pipeline external coating only. So enables one to carry out further tests to determine the status of the located faults. For example, maybe when you did the CIPS, you don't know exactly whether there's any coating defect or any other interference. So you can confirm that by doing the DCVG lah. So when the DC current flows in the soil to or from the bare steel in contact with the soil, a voltage gradient is established in the soil lah. So this voltage gradient increases with the defect size, pipe depth and soil resistance lah. So the larger the defect, it will produce this voltage gradient. So it uses a sensitive millivoltmeter to measure the voltage difference between two copper sulfate half cells. So basically it's just a normal voltmeter, but with a millivoltmeter sensitivity. Yeah. So you will walk along the pipeline and poke the ground on left and right side of your copper sulfate cells, half cells or probes. So the half cells are placed 1 or 2 meters apart, with the one half cell adapting a more positive potential lah. So and as a result, the direction of the current flow can be known lah. So during the survey, current interrupter shall be used. The on timer is shorter than the off timer. So when you go along the pipeline, you will know that the defect is, where is the location lah, by looking at the current flow. Okay. So the polarity of the applied CP can be recognized lah for the coating defect location. So he will walk along above or just side by side with the pipe. So as the defect is approached, the millivoltmeter will respond to the impressed current DC signal lah. So it will deflect in the direction of the current flow, which may be a defect or an anode system. So it can be a defect or can be a nearby or the anode system itself lah. So when the defect is passed, that needle deflection reverses and points in the opposite direction. So it means that you've already passed the defect location. So you know that the location where it changes from the positive going to the opposite direction. So you know that's the location of the ni lah. So where the needle shows no deflection, that would be the defect is located midway between these two probes lah. So that will be the location of your defects. So you will repeat again the DCVG at right angle. So you will turn 90 degrees, then you go forward and you go backwards from the point that you have identified earlier to confirm the two midpoints where it will intersect lah. Then you will mark the point with a wooden peg to locate the defect. So normally the defect is exposed coating. Normally it's exposed coating lah, like that. Okay. So for CP design considerations, so the design factors are as per RP NACE, National Association of Corrosion Engineers 0169-92. So this one might be old data. I'm sure there's something, some development within this last 10 years. So field survey and data, power source availability, nature of coating, polarization level, whether you want this to be 850 millivolts or 950 millivolts if there's sulfate reducing bacteria within the soil. And is there any earth electrodes near or along the pipeline, pipe crossing and valve pits and AC induced effects. This AC induced effects is mainly from if you are installing your pipeline along or near an intersection of a high voltage transmission line. Third is soil resistivity. This one will determine, but for ICCP this is not really an issue. Basically you can just install at any depth. You just need to apply the right voltage and current. And then the selection of the coating consideration with respect to CP. Different coatings will end up with different corrosion rate annually. So the better the coating, smaller corrosion rate will be assumed annually. And then whether you want to use the selection of CP lah. So this one will be depending on the how much current needs to be protected, required to protect the pipeline or the tank or any electrical equipment. Any metal equipment that needs cathodic protection. Protective current requirement depends on the coating type of the structure to be protected and the current density lah. So the current density will depend on the surface area that needs to be protected. Okay. So that is all, ladies and gentlemen, for part 3 of 3. So thanks again for watching. For any updates, do subscribe to my YouTube channel, Crux of EE, and then also my FB page, Facebook page, /Crux of EE, and I also have my website and Instagram. Any questions, do email to this email, and or you can leave your questions in the comments below. So this time around is on cathodic protection, not really related to the electrical world, but just want to share with you since it's quite good info lah for the rest of us. Okay, thank you again.